last class we started inverse functions. We talked a little bit about it, and I think it's not too hard of a concept, but there was the one question that I think made everyone a little bit confused on how to solve, especially at the end. So I do want to do a little bit more practice with that, so we're all kind of comfortable with solving inverse functions that have denominators in them too. And then we'll go and continue with class. So let's just do a little bit of review at the beginning of class today. So we talked about inverse functions. What do we remember about inverse functions? How do we find them? What do they do? Anyone recall anything about inverse functions? So if I'm given a question like this, how would I find the inverse function? Yeah, perfect, right? For inverse function, the way that we go about this is we switch x and y. That's essentially how you find the function. Of course, you have to solve for y after that, but the idea behind inverse functions isn't really too big of an idea. We just switch x's and y's and figure out what happens, okay? Who remembers how to tell if something has an inverse function? We had the graph. Horizontal line test, right? So we introduced the idea of not just the vertical line test, but the horizontal line test. And that test basically figured out if a function had an inverse or if it didn't. So determines if a function has an inverse. Right. I'll give you one, Olivia. Okay, so basically two things for inverse functions. All you have to know is switch x and y and horizontal line test. Cool. I want to do one example very similar to last class, just so we're on the same page with how we do inverse functions when there's a denominator, because I think the algebra kind of was a little bit scary, but I promise it's not too bad. So in this example, we have f of x equals 4 over x plus 2. Kind of hard to switch x and y's when there isn't a y. So maybe I should write y instead of f of x, right? We all know that f of x is another way of saying y. Okay, so that's kind of how we go about this first. Okay, and then of course, if we want to switch x and y, well, wherever I see a y, I'm going to write an x. And whenever I see an x, I'm going to write a y. Okay. So our next step is solving for y. Now, it looks a little scary because the y is in the denominator. I want to get y by itself, and I don't want it to be in the denominator. I want it to be in the numerator. So what do you think is a good step in getting y by itself here? Good. Multiply both sides by y plus 2. All right. Now that we're here, well, on the left-hand side, I have y plus 2 times x. And on the right-hand side, it looks like the y plus 2's cancel out, and I'm left with a 4. Okay. Now this looks really weird now because I have x's and y's on one side. I have 4 on the other side. Okay, any ideas on what we can do now? I could subtract an x on both sides, but it might make things a little bit more complicated because the x is actually multiplied, not added. Any other ideas? That's a good idea, right? We have two things that are multiplied together. And maybe I can FOIL this x over, or distribute the x over to the y and the 2. So I'm left with yx plus 2x equals 4. Okay. Now remember, my main goal is to get y by itself. I know there's x's floating around, but we still want to get y on its own. Okay. What do you think I should do to get y on one side and everything else on the other side? Dividing by x does work. I think it makes it a little bit more complicated to me. You know what? How about we do it both ways? Okay, so I'm going to do one way and another way, but that's actually a good idea. It isn't how my brain thinks, but it works. So let me write out Stephen's idea. And that's dividing by x. Okay, so I can take yx plus 2x, divide that by x, and I have 4 over x on the other side because I'm dividing by x on both sides. Okay. On the left-hand side, I'm going to get, let's see, y plus 2 because the x's individually cancel out. And on the right-hand side, I have an x. Okay. What can I do to get y by itself? Subtract 2, right? So move the 2 to the other side. And I'm left with this. So that's actually a totally okay way to do it. The reason why it was okay to divide by x is because both of these values had an x. So dividing by x made it really easy to separate the x's together. Okay. Let's go back to this step here. Okay, and I'm going to show you what I would think first. I think it's a little bit easier conceptually for me. I don't know why. So I'm just going to copy what I have here. Okay, so yx plus 2x equals 4. In my head, the easiest thing to do is to actually subtract the 2x on both sides. Okay, and you can do either way. And if we subtract 2x, we have yx equals negative 2x plus 4. Okay, now to get y by itself, what do we do? Divide by the x, right? So dividing by x on both sides, I am left with y equals negative 2x plus 4 over x. Okay. Kind of weird though, because I solved the equation in 2 different ways. I have this answer here and this answer here. Why did I get 2 different answers? Ainsley? Yeah, there's actually a way to simplify the second one. Now, if you leave it like it is on the right, that's fine. But let's just simplify this real quick, okay? I can divide the negative 2x over x to get negative 2. And I can divide the 4 by x to get 4 over x. And now you can kind of see that both ways would give you the same answer, okay? So either this answer, or this answer would be correct. I just kind of think it's more intuitive on the right-hand side, but if you want to do the left-hand way, that's okay too. Okay. Any questions on example number 1? All right. If you flip the page over, I have 2 very similar examples. There's something slightly different about these 2, but I think we can do that on our own. What I'm going to have you do is maybe I'll get you to get into groups of maybe like 2, 3, or 4. I'm going to assign your group a problem to start with, and then you can work on these together. So how are we going to do these groups? Maybe a group of 3 in the back. Maybe Ainsley and Tim, you can work together. Our answers real quick. So I don't know why I switched back to the last page there. Really nice job as I've been walking around. Looks like you guys are pretty good with this now. But let's just go over these 2 examples before we go on here. So example 1A looked like the last question, except there was a 5th power here, which I didn't put on the last slide or on the last example. So Ainsley wrote this one up, right? Do you want to take us through your steps? Mhm. Mhm. Perfect job. I actually got a nice question as I was walking around. We took the fifth root of both sides. Why isn't there a plus or minus here? Will? Yeah, right. We only do the plus or minus root, or sorry, the plus or minus when it's a square root, a fourth root, a sixth root, anything with an even power. That's when we do the plus or minus. If there's an odd root, we're not going to do the plus or minus here. Okay. Any questions on example 1A? Sounds good. Nice job on that as I've been walking around. Let's switch over to 1B. Will, do you want to take us through this one?
I switched it. And then both sides by y plus 1.
Mhm.
That led to y cubed plus 4. That turns into y cubed plus x. Y cubed x plus x equals 15.
Mhm.
Divided all that by x. Y cubed plus 1.
Mhm.
Subtract y cubed is 15 over x minus 2. That's
Mhm.
y equals
Perfect job. Any questions on either of the two examples here? Okay. Do we feel a little bit more comfortable finding inverse functions with denominators? Okay, that's my goal today. I think I saw a couple people being like, okay, I think I know what to do, but I'm not exactly sure what steps to do first. But I think we're all on the same page now, which makes me a very happy person. So now I feel a little bit more comfortable with moving on to our next topic of the day, which is a brand new section. So I actually have a brand new set of guided notes for you again. Let me get this passed out. All right. Oh, sorry about that. All right, anyone need more time writing this down? All right. Let's move on to this set of notes here. So we're starting a completely new section. We're moving on to talk about a very specific type of function, and then logarithms, which I think scares everyone. But I promise by the end of this section, it won't be as scary as it seems, at least to me, but it's easy for me to say, right? Okay, so I just kind of want to give an introduction to what exponential functions are, because we have worked with exponents before. So the word exponential might not seem any different to you, but it is, there's a slight difference, okay? We've worked with exponents before. We've seen, let me give you an example here. I think the first thing we did in class was taking a number like squared and raising it to the third power. And we said that we could multiply the two together and that would give us a to the 6, right? So exponents is something that we are very familiar with. Another time we've worked with exponents were our power functions. So we've seen f of x equals x squared and x cubed. Okay, so these are all functions with exponents. Let me show you what an exponential function is, and I think it'll clear things up. Okay, so this is an example of exponential functions. Functions like this, 3 to the x, 5 to the x, even things like pi to the x. Okay. So we've dealt with exponents and exponential or functions with exponents before, but in all these examples, the variable has been in the denominator, or not the denominator, in the base of the exponent, okay? And we haven't really messed around with the exponent on top, okay? When we have exponential functions, the base of the exponent is always going to be some sort of number. So it's going to be a constant like 3 or 5 or something like that. And in the power, we're going to have some sort of, it's either going to be x or maybe a polynomial, so x squared or x minus 1, something involving x in the exponent. Okay, so that's the difference between an exponential function and things that we've done before. Okay, so I'll just give you the textbook definition. I literally copied and pasted this out of the textbook. Remember, we call the bottom the base, right? So we usually say f of x equals a to the x, a representing some sort of number, x is just x, okay? And I'll show you what the graph looks like. It has a very unique shape to it, and it looks like this, okay? And the graph kind of depends on what a is, okay? So let's just say that a is something bigger than 1. So for example, 2 to the x, or 5 to the x, or even like 11.5 to the x. In all these examples, the base is bigger than 1, okay, like 2, 5, 11.5. Whenever we have this, the graph is going to go upwards. So it's going to look like the graph on the left, okay? Now we have a very specific name for graphs that look just like this, and we call it exponential growth. Okay, which I think a lot of you may have heard before. Okay, so exponential growth represents a graph that looks like this. Okay. Now, on the other hand, if our base is between 0 and 1, so for example, 1/2 to the x, or 0.25 to the x, or 7/8 to the x. Okay, whenever the base is less than 1, okay, our graph is actually going to go down. So our graph is going to look like this. And anyone know the term for this one? Exponential decay, good. Okay, exponential decay talks about when the graph goes down. It looks like it's decaying, right? Okay, so whenever we have a graph like this, we know it's going to have this shape. And I'm kind of going to tell you how to go about this. First of all, this graph has an asymptote, which is something the function gets close to but doesn't touch. And the asymptote is definitely the x-axis, right? It looks like this graph gets really, really close to the x-axis, but it never actually touches it. Okay. So what I want to do is some examples on how to graph this. With exponential functions, I know a lot of the times I tell you, okay, know the base function, and then if it's multiplied by something, like multiply it by the power and figure out what happens. With exponential functions, I recommend you to just plug in points and then follow the shape. And if you don't understand what I mean by that, let's do a small example and I'll kind of show you what I mean by this. Example 1, we want to graph y equals 2 to the x power. Okay, so I said the best bet is to plot some points. So I'll make a little x and y chart. Okay. I don't know, what sort of numbers should I plug in for x? Some easy numbers. 0. 0 is always a good one, right? 0 usually works out pretty well. Okay, so when x equals 0, y would be 2 to the 0, which is good, 1, right? Anything to the 0 power is always 1. Now, was it very special to the function to the x that when x equals 0, y was 1? Do you think if I changed 2 to a different number, it would be different? No, right? Because anything to the 0 power is always going to be 1. Okay, so there's one very special thing about exponential functions, if we're not shifting it or anything. When x is 0, y is always going to be 1. That's always going to be true for exponential functions. Okay, so that's one point we always know is going to be there. Okay, so maybe I should plot that, right? Okay. Let's plug in some more points. 1 is usually pretty good, right? So when x is 1, y is 2 to the first power, which is just 2, right? So I have another point, 1 comma 2 on my graph. Okay. Now let's talk negative numbers. Okay. Let's see what happens when x is equal to -1. Well, we have 2 to the power -1. What is that? 1/2, right? A negative power brings the number into the denominator. So this is actually the same thing as saying 1/2. Okay. So we have -1, 1/2. Now this is actually enough information for me to draw my graph. Of course, you can draw more and more points. I think as you can kind of tell, if I plugged in like x equals -2 and -3 and -4, the graph will get closer and closer and closer and closer to the x-axis. As I plug in higher numbers, the graph is going to get exponentially larger because we have an exponential function. Okay, so using the shape of my graph that I already know from the definition, my graph is kind of going to look like this. It's going to go up. And as we get towards negative values, the graph is going to get closer and closer to the x-axis. Okay. Now, this graph isn't actually going to touch the x-axis, so we're going to have an asymptote. Okay. So remember the word asymptote describes something that we can't really touch. Okay. Any questions on example 1? All right. I'm debating on if I should let you do. Yeah, I'll let you do example 2. I'll give you a few minutes for this, then we'll come back. All right, I know some of you are still working. I just wanted to give you some time to think about what the numbers might be here. But I do want to go over this kind of more thoroughly so we understand what's actually happening when we plug in our x values here. Okay, so we have x values and y values, and we probably want to figure out what they are. We always know that when x is 0, y is 1, right? That's always one point that we have on the exponential functions, okay? So this is always going to be true, okay? So I don't even need to do anything, and I know that point's going to be true. Okay. Now, 1 is probably the easiest point to plug in after that. If I plug in 1, we have 1/3 to the first power, which is 1/3, right? So x is 1, y is 1/3, which is about there. Okay, let's talk about what happens when x is -1. Okay, so when x is -1, we have 1/3 to the negative first power. Okay, what is that value?
3.
Just 3, right? Because when we take something to the -1 power, the top and bottom flip, right? So all we have to do is flip the numerator and denominator, and this turns into 3/1, which, as Stephen said, is 3. Okay, so whenever we have a fraction and we take it to a -1 power, it just flips over. Okay, so we have -1 comma 1/3. Now, I can plug in more points, but I think we're pretty good here. So I know what the shape is going to look like. I know that it's going to get closer and closer to the x-axis, which is my asymptote. And my graph is going to look somewhat like this. Okay, so I still have an asymptote here, which I guess I'll mark. All right. Any questions on drawing like basic exponential functions? All right, let's make it a little bit harder. Okay, so if we flip over to the next page, we have an exponential function that looks a little bit different than what we dealt with before. Okay, this time we have 3 to the x, but in the exponent, we don't just have x by itself, we have x minus 1. What do you think is going on here? Think about your test. And how do you know it was horizontal and not vertical? Yeah, right. There's a -1, and the 1 is kind of attached to the x, right? So Will said this is a horizontal shift. Is it going to the right or to the left?
Right.
To the right, right? When we subtract, it goes to the right. To the right 1. Okay. Let me show you what would happen if this was a vertical shift. Okay. So on the side, I'm going to write not the problem. Oh my God, I can't spell problem. Problem. There we go. This is not the problem. I'm just going to give you a separate equation. Okay. If this was y equals 3 to the x plus 1, this would be a vertical shift. Okay, because the 1 is being added to the entire function. Okay, so this is an example of a vertical shift up 1. Okay, so that's the difference between a vertical and a horizontal shift here. Okay, so we are horizontally shifting a graph. What's our original graph that we're actually shifting? Yeah, 3 to the x, right? 3 to the x is a very basic exponential function. So maybe I should draw y equals 3 to the x. That sounds like a good place to start here. Okay, so the way that we do that is by making our x and y points. Now, I'm sure some of you can do this in your head, but let's just go through this real quick. Okay, I already know that 0, 1 is a point, right? That's already something that we know. Okay, so that's here. I definitely can plug in x equals 1, which would give me 3 to the 1, or 3. Okay, so that goes here. And then I guess I can plug in -1, which would give me 3 to the -1, or 1/3. Okay, so -1, 1/3 would be here. Okay, so this is an example of exponential growth because the graph is going up. My graph is going to look like that exponential function, so it's going to look like this. And we've got the x-axis as our asymptote. Okay. So horizontal shift to the right 1, we're used to doing this. Take every point and shift it to the right. So I'm going to take this point and shift it over 1. So we have 2, 3. I'm going to take this point and shift it over 1. So we have 1, 1. And then I'm going to take this small point here and move it over 1. So we have 0, 1/3. Now, we can also take our x-axis or our asymptote and shift it over to the right. But since it's a horizontal line, shifting a horizontal line to the right isn't going to do anything, right? So that's going to go here. All right. All we have to do is connect our dots. And this is my new exponential function. Any question on these guys here? All right. You know what? I think the next I want to spend more time on the next thing that we're going to do here. So I think I'm going to leave it here. Next time we're going to talk about exponential growth and the natural exponential function. But I think I'll leave it here. So I'll let you out a little bit early.